to all. Today we will discuss about introduction to tree. In data structure, there is two different types, that is linear data structure and non-linear data structure. We can discuss in linear data structures, and now we can discuss about non-linear data structures, that is trees and graphs. Firstly, we can discuss about trees. A tree data structure is a non-linear data structure because it does not a sequential manner. It is a hierarchical structure, has elements in a tree are arranged in multiple levels. The tree has following some parts, that is root, child node, parents, siblings, leaf node, internal node, ancestors node, descendant nodes. Now these are the root node, that is 1, and parent node, that is 2, and internal nodes are there, and child nodes and siblings and ancestor node. These are the 10 types of nodes in a tree. Now different types of trees are available in data structures, that is first one is general tree. So general tree means these trees are hierarchically placed one and another. Every node have infinite numbers of children in the child general tree. That is, A has become 2 children, and B becomes 2 children, and C become 2 children. That is A becomes 2 children, that is P and C, that is T1 and T2, and B have 2 children, that is D and E, and C have 2 children, that is F and G. Now this is the binary tree of a tree. Second one is the binary tree is kind of tree which 2 children can be found for each parent. So every parent must have 2 children. This is more popular than most other trees. The binary tree have very important to another. So first one is we can give parent node, and we should compulsory have 2 children. So these are the binary tree structure. Now binary tree is used to binary search tree extension, which is several options are restricted. The left child value of the node should be less than or equal to the parent value, and the right child value should be always be greater than to the equal to the parent value. The BST, that is nothing but binary search tree, makes it deals for the searching operations. We can accurately terminate it to each node whether the values is the right subtree, this is the search tree. And next one is AVL tree, that is Adelson, Welsh and Landis tree. The AVL tree is also called as a binary tree. The tree self-balancing on behalf of the inventors. In this tree, we can use first tree that balancing dynamically. A balancing factors are allocated to each node in the AVL tree based on the whether tree is balanced or not. In this tree, we can use a value and a parent tree and child trees and child to subtrees, subtrees to another subtrees are in there. There is AVL balance self-balancing, that is only one child or child not and parent child, etc. And now discuss about what is the binary tree. In these trees, we, as you know, the general tree, the binary tree, the binary search tree and AVL tree, these 4 are the different types of trees available in data structures. In this binary tree, we can use most 2 children can be found for each parent. So there must and should 2 children are in the one parent. The kids are known as left kid and right kid. The kids are given left and right kids. In this popular, the most of the trees, each node contains some components, that is pointer to left subtree, pointer to right subtree. Third one is data element. In this pointer to left subtree are the children's, pointer to left right subtree are the another children, that is another kid, and the data element is the in this representation of the tree. Now what is the in this tree we can use left and right, that is middle data. In this left and right A we have two children, that is B and C. So this is the binary tree representation. In this B we can given D only, that is left side, and the C we can given E and F, they are two children. Now we can discussing about some common terminologies of binary tree, that is root node, parent node, child node, leaf or external node, internal node, depth of a node, height of a node. First we discuss about what is the root of a node. The topmost node in a tree is called a root node. The parent node is a tree connected by a direct edge from the exactly one another end. These are called a parent node. And the child node is directly connected to another node when moving away from the root. And the leaf or external nodes are which have no children, and internal node at least one children, and the depth of the node is number of edges root to the nodes, and the height of the node is the number of edges to the nodes to the leaf and the height of the tree. Here we will discuss the root node, the subroot node, and the subchildrens. The tree has 10 nodes with 5 internal nodes, that is A, B, C, E, F. A have two children, that is B and C, and C have two children, that is E and F. Now D external nodes are D, F, H, I, G. The height of the tree is 3. The external nodes are D, E, F, D, F, H, I, J. The height of the tree is 3. The B is the parent of D and E, and while D, the children are E and B. So let's discuss about the binary tree implementation. In this implementation, we can use to pointers concept with the help of implementing the binary tree. The first node in the tree is represented by the root pointer, that is called root node. Each node in the tree consists of 3 parts, that is data part and left pointer part and the right pointer part. To create a binary tree, we first need to create the node. We will create the node to the user defined, that is struct node into data, struct node into left into right. In the above structure, the data and the left pointer and the right pointers are the address of the left node and the address of the right node. Now, binary tree traverser is used to examine the list of a simpler structure, can be traversed either forward or backward directions. In this, what order to be visit node in a tree? The most common trees are traversed orders, that is pre-order, in-order and post-order. In this pre-order, in-order, post-order or traverser to the algorithm, we have to know process node, process left subtree, process right subtree. And the traversal order is determined by the order these operations are done by the binary tree traverser. The most common points are pre-order, in-order, post-order. The pre-order is denoted as node, left subnode and right subnode, and the in-order defined as left subnode, node, right, and the post-order is defined as left, right, node. In this pre-order, in-order, post-order, we can use stacks in arithmetic expressions, that is infix, prefix and postfix. Now we can discuss about a pre-order binary tree traverser. In the pre-order binary tree traverser, we can use process order of node, left subtree and the right subtree. Void reorders. The struct node is not equal to 0. The process of node is value. The pre-order is node to left and the pre-order node is right. The example result is PSAMAEL RTEE. These are the pre-order binary tree traverses. So the pointing towards the arrow marks is given to is PSA, and then A is given to M, and M to M go to and A go to E, and E go to L, and L go to R, and R go to T, and T go to E, and E go to E. That is the example of pre-order binary tree traversal. Now, the example of a post-order binary tree traversal. The process of order of a left subtree and a right subtree nodes. We will in this post-order binary tree. So void post-order struct node into node. If node not equal to 0, the node can be left, the node can be right, or node can be a variable. Example is A. So first node in the left side is A, go to A, go to M, go to S, S to L, L to T, T to E, E to E, and R to E, E to P. So this circle is going to like this, the blue color circle. So this is the example of post-order binary tree traversal. Now the example of in-order binary tree traversal. The process of order of a left subtree node and right subtree. The void in order is struct node into node. If node not equal to 0, the node is left and process is node to value, and in order is node to right. The example is A to S, S to A to M, M to P, P to L, L to E, E to T, T to R, E to E, and E to E. This is, so firstly we can give A value, and A value to S value. The blue line is arrow marked in this diagram, A to S, and S can be converted into A to M, then go to A to M, then M go to P, and P go to L go to E, and E go to T, and T go to R, and R go to E, and E go to E. This is the in-order binary tree traversal example. Now, let us discuss about what is the binary search tree. The binary search tree is a special type of binary tree that has special order of elements. There are three basic properties of binary search tree. That is, left subtree of the node should have a value less than the node value, and all the right subtree of the node should have the value greater than the equal to the node values. Both the left and right subtrees should be binary search traversal in. This rule can be applied from recursively. So these are the binary search tree example. So we can give root node is 30 and 2 child node, that is 15 plus 60, and 15 we will given 2 child node, that is 7 to 22, and 60 we can given 2 child node, that is 45 to 75. In left sub no in the right sub child node 22 we can given 2 sub children, that is 17 to 27. This is the binary search tree traversal. Now discuss about what are the operations of binary search tree. So first one, we can insertion and we can deletion of a binary search tree, and convention to even after the performing all the operations to the performed in the binary search tree. First one is searching. So searching is we need to search for an element to traverse the entire tree. We can optimize the using his properties. So the basic idea of the searching the item is BST. When we compare with the root node of the tree, the left three cases is described. That is, item is equal to root dot value, that is item greater than root dot value, that is item less than root dot value. So item equal to value is terminated to the item is founded, and item greater than root value is we just check the right subtree because of all the values to the left subtree. that is root dot value, and item less than root value is just check left subspace of the complexity values. Now discuss about how to implement the binary search tree. Now given some problem, our objective should return the true value if the node existing with the value equal to the item, else it returns false. Now check if the root node is null, return false, else compare root dot value and item is equal to root, that value returns the true, and the item less than root value the recursive for the left subtree, and item greater than root value then recurs for right subtree. Let's the example of pseudo code, that is boolean search free node int. So these are the small example from binary search tree. Now let's discuss about the second operation of binary search tree, that is insertion. So first point is searching and second point is insertion. Let's see, the insertion of binary tree is done at the leaf, but it need to maintain the properties of binary tree to decide in this case. Solutions or steps. We need to insert a node from the value items and return to the root node new modified tree. If the root is null, the new node will be return the item, and else compare the item with the root value. If the root value is less than item, then go to right subtree. If the root value greater than item, then go to left subtree. These are the another example of pseudo code. Now the third operation that is performed in deletion operation of binary search tree is the node can be deleted in a leaf node. The node can be deleted as only one child. The node can be deleted as both child. First we can use the node can be deleted in the leaf node is simply remove the node from the tree. That is so simple from it. Then the node to be deleted has only one child. Replace the node by its child. The node can be deleted as both children's. The node still need to be replaced and maintain the BST properties. Which node should replace the deleted node? Suppose we have to delete the node with the value of 6. Which node should be selected ideally to replace this node? That is 6. Now the solutions and steps for deleting the node with the item and return the root of the modified tree. First we need to find out the node can be deleted and replace it by the appropriate node if it needed or not. First one, check if the root node is null. If it is, just return the root itself. It's an empty tree. If root dot value less than item, recurs to the right subtree. If root dot value less than item, recurs to the left subtree. If the both have conditions above false, that means root dot value equal to item. Now we first need to check how many childs did root have. Case 1 no child, case 2 one child, case 3 two children. One child, there is one child, replace root by its child. There is no child, just delete roots or deallocate the space occupies. There is two children. And now discuss about the graphs. A graph is consists of a finite set of vertices, that is nothing but nodes, and the set of edges which is connected to a pair of nodes. It is represented as edges which communicate that x vertices and the y vertices. So as you know, all of you, graph is the x and y vertices are in there, and some edges are given to the graph. The structure is a collection of nodes that have data or connected to one another. A collection of vertices are called V. A collection of edges are called E. Representation of the other pairs of the vertices U comma V. That is V is equal to 0, 1, 2, 3, and E is the combination of 0, 1, 0, 2, 0, 3 and 1 and 2. Next, graph data structure. Can be represented in a data structure. We can represent graph using array of vertices and a two-dimensional array of the edges before we proceeded to others. In this graph we have two types, that is directed graph and undirected graph. In this directed graph we We have not given the arrows, and the directed graph we have given arrows, particular arrows. An undirected graph edges are not associated with the directions with them. There is no directions given from the undirected graphs, and the directed graphs were given to the direction from the directed graphs. Thank you.